Today we will cover, today's chapter 3. So this is chapter 3 in your textbook. We will cover all of chapter 3 today. We will review it again on Monday, and we will work homework and a few other items that we'll need to do. So practice things that you'll see here today. We're going to actually practice those things on Monday. So if it's math related, that will probably go into Monday's lecture. Got it? So for the most part, that's how it will go. Chapter 3 is a standalone chapter, standalone exam. This is perhaps all of my slides are for the study guides. Okay, so if you look at the slides, you're seeing the study guide for the most part. If you follow the slides and you memorize most of the material there or learn the material, you'll do pretty good. Chapter 3, almost everything from every slide is on. There's a question for every slide on chapter 3. Got it? So you will want to look at absolutely every slide in chapter 3. If there's something that's not there, I'll try to make sure I note it as we go through here, and I'll try to tell you what's the things to specifically look for. But for the most part, chapter 3 is one of those chapters. You look at the slides, and it goes by pretty much that way. There will be, for 102B, there will be, again, the questions from homework on the exam as well. Everybody follow where we are? That's how it will work. All right, let's get going with chapter 3. Chapter 3, radiation from the sun. How is sunlight measured? We're going to learn about that. What types of radiation are more energetic than others? And that's going to be pretty interesting to talk about, particularly with the arguments about how cell phones affect us, things of that nature. What is the link between sun exposure and sun cancer? There's a link there. How does Earth's atmosphere naturally protect us from the sun? The Earth was created, designed, or evolved, whichever one you choose to believe, in such a way that it favors humanity, okay? And so we're going to talk about how that is and why that is and how we protect that. Can this source of natural protection be eliminated? And if so, can it be restored? The answer to that question is yes, it can be, and yes, it can be restored. And how does sunscreens and sunblocks work? So we're going to talk about those as well. Again, we will cover all of chapter 3 today. I'm not sure exactly what pace, but we will cover it all, and we will review it again on Monday with more detail. So each time I do a review, there's more detail that we give you. Follow? All right? And also Monday will be your prep for your exam on that Wednesday. We will have the exam on Wednesday. Okay. This chapter focuses on radiation from the sun, electromagnetic radiation. Absolutely everything on this first slide will be covered in some fashion. There will be a question on your question. So for the most part, for most of these slides, you're going to hear me repeating that. So if I stop saying it, most of it's going to be there. This is your complete study guide, chapter 3. All right? Short electromagnetic radiation with waves composed of both electric and magnetic, and that's important. It's not just electric and it's not just magnetic. It is a combination of the two. All right? So it's electromagnetic. Not only does it have zapping power, but it has magnetic power, meaning there are electrons there ready to do things that electrons do, and you're going to learn more about how electrons work, particularly when we start talking about valence electrons. So it's a combination of the electric properties and the magnetic properties. Both are the result of electrons. Got it? Now we know that electricity specifically involves movement, 3D movement of electrons. So it's like electrons running along a conduit, okay, or ants running across the lawn. So that's specific there. So that's a movement of 3D. In terms of magnetic, it has to do with the position of electrons and things of that nature, okay? So when we talk about radiation, there's short-range radiation, visible, infrared, and magnetic waves. You're going to learn the others when we look at the complete spectrum. But these are the critical ones that we hear a lot about. Well, okay, so we have them all included here. Short-range, visible, infrared, and microwave. So these are the 4 major areas that we are going to discuss. So your short range includes UV, okay, ultraviolet, X-rays, gamma rays, cause rupture of molecules and bonds. The short range radiation are the most harmful to organic matter and harmful to human beings, okay? So when we look at UV radiation here, X-rays, X-rays, that's when you go to the dentist, and the your dental hygienist puts the device up against your face, and then she puts a tape on, and then she runs out of the room. No, she doesn't exactly run out, but she leaves the room. Okay, these are X-rays. Okay, so that's there protecting. This is why they ask you whether or not you're pregnant and things of that nature, because the damage that it might do to the fetus, things of that nature. So X-rays X-rays can be harmful, but it's when properly used, is very helpful to us, and you know how it's used to take X-rays. Gamma, that's the Incredible Hulk. Okay, so gamma radiation, you get turned into the Incredible Hulk. Gamma radiation is a harmful fashion. It ruptures molecules and bonds. And then we have visible. Invisible, does anyone have component cables still other than the MIDI cables in your television? Anybody know what component cables are? The green, blue, yellow, red, those cables? Okay, look at the back of your DVD, all right? That's what this is, okay? So that's, all right, so that's your splitting. That's what's happening in terms of this projector as well. So this is your visible light. Used for photosynthesis and solar applications. So photosynthesis is how organic matter was formed on Earth. It was through a process of photosynthesis. So this is pretty important to life and to being visible. Essentially, what happens, we get a reflection back to our eyes. It receives it, and then it analyzes it, and it says, "Wow, that's green, that's red, that's yellow." Well, it's really the light it's how we detect it. Follow? But so this is your visible light, and then you have infrared. Infrared is the longest of the visible spectrum, causes molecules to bend and stretch. So this is used in your I think you guys in lab will probably do some IRs. So when you do IR, this is what's happening in an infrared spectrophotometer. It bends the molecule and it stretches it. And when it does that, it reads a frequency. Okay, so at a certain frequency of light, it causes a certain molecule to bend or stretch. And some really smart people developed an algorithm, or developed a way of actually, some mathematicians, of figuring out what that meant, and it gives you a interference curve. It gives you a curve, and that's what we read it as. So when it matches that frequency, we get a response. Okay, it's called detection. So infrared. So infrared's there. Now, the other one then is microwave, cause molecules to rotate. And because they rotate so fast, they give off heat. That's why you could pop your popcorn and make your tea in your microwave oven. Okay? Because the molecules are rotating. So we can differentiate between infrared and microwave by rotation of molecules or by bending and stretching of molecules. And that's a pretty important scientific concept to hang on to. So this is what this spectrum looks like, and this is pretty important because this is life on Earth. Okay? We have short range electromagnetic radiation, we have visible, we have infrared, we have microwave. Again, electromagnetic radiation are waves composed of both electric and magnetic fields. That's a great type true-false question that I like to ask. So let's look at this a bit further. Electromagnetic radiation. Wavelength we call lambda. The wavelength is the distance traveled between successive peaks. All right, so it has a start and end point, and that's what defines a lambda, is that distance. Okay, it's like a 100-meter run. It's between the starting gate and the finishing lines. That constitutes one 100-meter run. For electromagnetic radiation, lambda defines that distance. Okay, and so when we look at it on this particular slide, we notice where it's labeled here from lambda, from top to top. You could actually do this from bottoms to bottoms. You follow? All right, so that's one lambda. You could do it from any other point, but typically people just customarily like to start here. And you guys have seen these waves if you've taken any type of trigonometry. So this is really your trig waves. This is why you did all that trigonometry in high school and doing it at Saginaw Valley State University. So you would know how to properly do a wave, okay? All right? And no, it's a little different from the wave at the football game. All right? So this is what it looks like. Now, What's important about this? So we have the wavelength. Does everyone follow wavelength? Right? So we go from top to top, right? Note so that's the red curve. Note the purple curve on the bottom. We still have a wavelength, right? Does everyone see that? But this wavelength is shorter than that wavelength. You follow? So you can have short wavelength, long wavelengths, which is what you learned in the first slide. You have shorter wavelengths and longer wavelengths. Now, here's what happens though. As the wavelength gets shorter, the frequency increases. So wavelength and frequency are inversely proportional. So longer wavelength, lower frequency, shorter wavelength, higher frequency. So frequency, it equals the number of waves passing through a fixed point in 1 second. So it's the number of waves that are passed through per second. And a reciprocal second is called a hertz, and you hear about hertz when those of you who like to play around with music a lot, right? So you hear about hertz and kilohertz and things of that nature. That's what it's talking about there. It's talking about its frequency, okay? So wavelength and frequencies of electromagnetic stereo are related by nu equals the speed of light divided by lambda, okay? All right? So this math, for those of you who understand the math, and if you don't grasp the math, then visit the math center, and they'll help walk you through it. This helps you to understand that what? The frequency is inversely proportional to the wavelength. You get it? Right? Recall that from math? Somewhere, right? And frequency is directly proportional to the speed of light. All right? So, here's what we discovered then. Let's review it. So wavelength is what? From hilltop to hilltop, from one point on the curve to the matching point on the other, or you can go from valley to valley. If that is stretched out, that's a lower frequency. If you take that same wave and push in the accordion, so it's a little bit like an accordion. Okay? You know what an accordion is, right? Yeah. So you got, okay, just want to check that, right? So I don't need to tell you something like I once played with an accordion band in the Swiss Alps, right? I did, yeah. I didn't speak any Flemish at all, and they spoke very little English, but boy, did we have a good time. Anyway, so it's an accordion. All right, there's my story. All right. So you stretch it out, it's a longer wavelength, right? What? Lower frequency. You press the accordion in. You get it? Shorter wavelength, but higher frequency. Higher frequency is more damaging than lower frequency. You get it? Longer wavelengths are better than shorter wavelengths towards biomatter. Okay? That's a very important concept to hang on to. So I think we're going to show you in the next slide here. Yep, the entire electromagnetic spectrum. So we take these concepts of knowing that they're short, visible, infrared, microwave. We take this concept of knowing that there are long wavelengths and there are shorter wavelengths, lower frequency, higher frequency, because this passes through a fixed point. More of these waves pass through the fixed point. Therefore, it has a little more impact, higher frequency. And now we put it together in one complete spectrum. And we're going to take time, we're going to walk through, we're going to talk about this in more in detail. If we take a look at this slide, electromagnetic spectra, on the left side, we have what? This is going to be what? Higher frequency. Does everyone follow that? More waves. Does everyone see it? Higher frequency, and this is going to be what? Lower frequency. Shorter wavelength on the left side, longer wavelength on the right side. This is complete spectrum. Let's start in the middle. This is where we are. This is where we enjoy life. From 400 to 700. We enjoy across this, but this is the visible. Okay, we get to enjoy the beauty of our surroundings. So the beauty of our surroundings is for the most part defined between 400 and 700. Okay, nanometers. This is called the visible region. So this is you. This is what you see every day. Okay. And some see the colors better than others. Now, over here, notice we move to the left. So here, as we move to the left to shorter wavelength, higher frequency, we get UV, which is very helpful. UV is the black light kind of thing. Okay, now there's even different frequencies for UV, by the way. At the beauty salons, at the spas, they have these black lights. You know, you get your nails done, right? It's time for me to get mine and my feet too as well. Okay. All right. Anyway, you get these done right, and you put them under the light, right? That UV light isn't that the intensity isn't. It's not as high frequency as when we talk about UV. You follow? So be aware of that. Okay. The black light at the nightclubs, again, not quite as high frequency. Okay. That type of light tends to rest right on the edge of visible. Okay. That way, otherwise, if you don't have on glasses to block it, it's not that intense. Does everyone follow? Okay. But it's also, but it's not. We don't advise you looking into it at all. Just staring into it. Follow? Okay. All right. So not quite as intense. Then over here, X-rays. Again, this is where the hygienist puts a lead apron on you and goes out the room and takes X-rays of your teeth. Okay. Then gamma is when you're really trying to destroy some biomatter here. Okay. Again, gamma. This is Incredible Hulk. This is the movie. This is where it's made out here. But these are very damaging. And so right here, so we move from very damaging to something that's not so damaging. Does everyone follow? And we move into visible. And we're going to talk about what the UV radiation that's coming through that does cause some damage to us. You're going to learn that. Does everyone follow? And it's a very important concept because we're going to make some points about how these are used. So let's go here. So then we have infrared. This is used for a lot of heating type of applications. Okay. This is also the small pointers, and this is also SWAT. Then we have microwave. This is for your popcorn. Okay. It's okay. And then we have radio. This is grandpa and grandma's old FM 107.1. You're listening here to Sirius radio. Get it? Grandma, grandpa are listening here to FM, AM radio. Follow? Okay? Have you heard of a shortwave radio? Have you ever heard the term shortwave radio? That's what this is. Okay? So we get into this right now. This is important. For the most part, unless there's extreme focus, the radiation to the right side are less harmful than the radiation to the left side. You get it? For the most part, we don't consider these to be harmful at all. But, now, by the way, Dr. Anthony Revis does not give medical advice. Got it? All right, everybody clear on that? I do not give medical advice. I don't do it. I just teach science. Follow? Now, there is some thought that your cell phone is causing cancer. Please stop sleeping with the cell phone because it causes cancer. Anybody heard? You guys have heard that? So it's a big panic for a lot of people, and a lot of people are making a lot of money selling a lot of shields that you can cell phone in to protect you from the radiation. There's even a YouTube out there that if you surround popcorn, we should probably do that one day. Surround popcorn with enough cell phones and look at it. It'll pop the popcorn. Anybody saw that video? Oh, you didn't? You missed it. It's out on YouTube, of course. It's on the net. It's got to be true, right? Yeah. That is not the type of energy that's used in cell phones, people. You got it? Okay. So you can buy whatever device you want. You can believe whatever you want to believe. But if you put that on my exam, the answer is going to be wrong. You got it? Does everyone follow? That is not true science that you're seeing. Okay? There is no scientific evidence that cell phones are causing brain damage. So even one YouTube out there, don't put it near your head. See how it zapped that popcorn? It'll zap your brain. But if you buy this cover for it, for only $9.99, put your cell phone in it, it'll protect you. Okay? Does everyone follow? Does everyone follow? This is where cell phones are. This is damaging into the spectrum. This is not. This is the useful part that we get to help enjoy and do things with. We do science here. We enjoy cooking popcorn here. And Grandma and Grandpa listen to the radio here. Does everyone follow? Okay? Is that clear enough? So if on the exam we ask where's the damaging part of the rays, if anyone puts circles radio waves as a damaging ones, I'm just going to take off a lot of points. I'm just going to stop grading your paper and stop right there. Okay, you're not going to get any more points out of it. Does everyone follow? The damaging side of it is to the left side, 10 to the minus 14. On the 10 to the, when you're going toward the 10 to the 2, these are less damaging. Does everyone follow? Okay, so be aware of that. When we look at the distribution of the energy from the sun, of the sun's radiation reaching the Earth, approximately 53% is infrared. That's heat. So we get heat, infrared. Follow? So let's go back to this electromagnetic spectrum. We're talking about infrared. Question for you, is heat a good thing? Good? Yeah, you got it? So these are the ones. Once you pass here, this is where we get to enjoy, and this is good. Okay, got it? This is healthy. So so 53% is heating. That's important to the Earth. 39% is visible light. That's really important, right? Because without this visible light, you will not get to enjoy. You could still hear my voice, but you wouldn't get to enjoy the visuals that goes with it. Okay? And 8% is UV, and this is the part that concerns us for our health. It is important to the function of the Earth. Does everyone follow? Okay? But it can also, if overexposed, cause some problems. And that's what we're going to talk a lot more about. We're going to actually talk about UV and infrared. We're going to talk more about infrared in some later chapters when we start talking about greenhouse effects. We'll start to mention it some today, but you'll hear this throughout the rest of the semester. There's probably this slide, I'm going back through the slides. The first slides I've been through, I'm on, I think it's the fourth slide. All of these important slides with concepts. So everyone follow. Now, so we know we have UV, infrared, and visible. So how does this electromagnetic energy, how does it operate around us? Okay, radiation may be described both as a wave-like and a particle. Does everyone follow? It has wave. Wave means it's like the sine wave, the cosine wave, or like the waves of the ocean. You got it? It moves on a wave. But it also moves in bursts called quantized energy. It's like a fist punch, another fist punch. But those fist punch come on waves. You got it? It's moving on a wave, each punch. Okay? The quantized energy, so this author likes to draw it as water and steps for quantized energy. That's kind of cool and cute, but I suggest to you that my example may help you a little bit better. Does anyone have a refrigerator at home? Does your refrigerator have the water and ice maker thing in it? Most of them do. If you don't have water and ice in it, that's probably a cabin refrigerator, right? So let's not the cabin, not the one up, where you go hunting. So you have it, right? When you want water, you push the one with the water, right? And what happens? It comes out of the stream. Does everyone follow? Okay? That's a continuous flow. Okay? When you punch the ice maker, it comes out cubes. It comes out chunks of cubes. The chunks of cubes are quantized energy. That's how energy moves. And it moves in those chunks of those cubes on a wave. So if you could somehow see the wave when it's coming at you, like see the light coming at you, or see the energy coming at you, if you could see it, it would look like chunks of ice on a wave. It would look similar like if you had a line of dolphins coming across the ocean, up and down. Does everyone follow? That's what it looks like. Okay. Now you've heard and you've seen quantized energy, right? Okay. Did anyone see what's a galaxy universe with a squirrel in it? Guardians of the Galaxy. Yeah, anybody see that? Okay, anyone see Star Wars? All right, if anybody see Star Trek? See, I knew you were going to say no. See, that's just, you start dating yourself, you say you saw Star Trek, right? If you saw Star Trek, it was with your grandpa, okay? All right? But that burst of pew, 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 that's quantized energy. Does everyone follow? But what you can't see is that it's moving like this. When it hits the guy, that's the burst of energy. That's the quantized. They get hit with these bursts of quantized. So that's what's happening. That's what it should be. That's what it's intended to simulate. So you've seen it before. If you've been to the movies, you saw it. So next time you go to movies, you guys are going to stop the entire movie just so you can talk about the chemistry and science of it. Yeah, I know. You can't wait to get home, go on a date, and say, look, let me tell you about quantized energy, right? I feel you, okay? That's what it is. It is bursts of discrete energy at certain frequencies, okay, of energy. Does anyone have a grandpa had an old radio where he said he'd dial it? No. You guys need to visit your grandpas more. Okay. They would sit there, would dial the radio and go, right? That's looking for the frequency match. And when it matches it, he can now hear it, right? Or if you had a grandma that had rabbit antennas, call them rabbit ears on the television, all right? Yeah, and she's like, and she's not going to change it, right? She's going to tell you, go change it for me. So you're doing this, you're trying to match the frequencies with it. That's what's happening here, and that's what quantized energy does. It matches those frequencies, moving on a wave, discrete ice cubes. Get it? So we match frequencies. When we look at the electromagnetic spectrum, we want to do something here. We match that frequency. We match the microwave frequency. We match the radio frequency. And this is what you do when you're dialing your radio. This is when you're setting your Sirius to Sirius 56. That is an exact frequency. Each of your cell phones has an exact frequency. That's why we don't cross signals with getting someone else's phone call. These are all exact frequencies and frequency matches, and the energy of these travel on waves, but they're quantized. So if it hits you, you get knocked over like Guardians of the Galaxy. Okay? Another way to view electromagnetic radiation is essentially by combustion or by burning it. The energy of radiation is related to the wavelength and frequency, and that's what we're talking about. How much energy is there based on the wavelength and the frequency? And we do a frequency match, okay? We do either short waves, or long waves. For instance, a blue flame is hotter than a red orange. This is how we see it, okay? Energy is proportional to the frequency, and it's inverse proportional to the wavelength. You will want to know this, okay? This is a slide with the burning flames on it. Here we have energy equals hc over lambda, E equals hc. This is a constant. This is a fudge factor that's put here to make the values work out. A really smart mathematician figured out that you needed this constant, Planck's constant, to help the math make sense. So here we have Planck's constant, speed of light over lambda, and voila, we get the energy. So this helps us to understand again that energy is related to the wavelength and the frequency, and that's the type of true-false question that I've been known to ask you. So let's look further at the types of UV radiation. Let's go back to this slide. We have what? Visible, right? That's what we get to enjoy and see. Infrared is what? Heat, right? And UV. And we know that UV is on the left side of the visible, okay? Right? So it could be what? More harmful. On the right side, less harmful. Left side, more harmful, okay? So now let's look at these in detail. You will want to look at this slide. And yes, I expect you to, for the most part, know everything on here. The only thing I occasionally let you get away with is here with the wavelengths. I typically ask you whether it's low, medium, or high, and I expect you to know a few things about the comments. But I do expect you to know that visible, I don't like to miss visible, is from 400 to 700. Does everyone follow? So I expect you to know that the visible wavelength is from 400 to 700. So you would know if it's less than 400, it's what? UV, X-ray, gamma. Does everyone follow? Greater than 700, we're into what? Infrared, microwave, radio wave. So I do expect you to know 400 to 700. On this particular one, the type and the relative energy are what's most important to making sure you get. I always ask that. I rarely ask for the wavelengths other than the visible for Chem 102B. If you were taking one of the upper level courses, you absolutely everything on this slide. Okay, so you have UVA, UVB, UVC. That's it. Those are the three we talk about. Okay, let's start with UVC. It is the most dangerous. Okay, all right. It is the most dangerous against. When we talk about most dangerous, we're talking against biomatter, against people, against humans. Okay, against your cells, against your skin, etc. Does everyone follow? So if I say most dangerous, that's what we're talking about. UV is very dangerous, but completely absorbed by ozone and oxygen in the stratosphere. Did everyone catch that? It's the highest, but does it reach the Earth? What's the answer to that? No. And that's critical to understand. Is everyone with me? So I always start each time I give this lecture with that part. UVC is completely blocked by ozone and oxygen where? In the stratosphere. We know the layers, right? We know we live in the what? Troposphere. You got that right on the last exam, I'm sure. Ozone is in the stratosphere. You follow? So ozone and oxygen in the stratosphere is blocking UVC. What do we know about UVC? It's the most dangerous. So what do you think happens if there's no ozone and no oxygen? Wouldn't be here. Wouldn't be good for us at all, would it? Does everyone follow? Okay? It completely blocks it. And that's critical to know. Okay? So we need the ozone layer. Does everyone follow? Without it, the radiation, we would have more skin cancer and things of that nature. And you're going to learn about that in some more slides to come. All right? So that's UVC. Then we have UVB. I just want to walk from bottom up. CBA is what I like to talk about it. So the highest, and then the medium is UVB. UVB is absorbed by ozone in the stratosphere. Most UVB, I apologize, is absorbed in the ozone. Okay? UVB is dangerous to the outermost layers of the skin. All right, so the outer skin, UVB, most of it, but does some come through? The answer is yes. So of the radiation that we talk about, A, B, and C, C is completely blocked. B and A are the only ones that come through the ozone. Everyone follow? That's important to know. And it has in terms of relative energy, it's somewhat medium. And then we have UVA, reaches Earth's surface in the greatest quantity and penetrates further into the skin. You get that? Now, it has less energy, but it penetrates into the skin, which means it can lay there, and you're going to see on some more slides. It can lay there over years. So it may take a little bit longer, but it can cause damage. So here's a question for you. If I were to design a skin blocker, okay, and let's say I have skin block, I have two formulations. I have one with A and B. Then I have one with A, B, and C. All right? Skin block A costs $10. Okay? However, I'm going to give you the added benefit of formulating my sunblock that blocks C. And don't worry, it's only going to be $25. Which would you buy? First one? Anybody buy the second one? Why? That's right. You get it? Why? Ozone, nature, life is taking care of that part for you. If it's there, great. But $25, it's like it doesn't have an effect on you. Does everyone follow? When the ozone's doing its job and oxygen, when the stratosphere is working properly, which is why we talk about protecting our environment. When it's working properly, we don't worry about UVC. However, A and B, we worry about. We're concerned about. You follow? So be aware of that. That's the science. Okay? So if there's an infomercial on in the middle of the night, you got to tell you, look, I have this great new UVC. All the other guys have been leaving this out of their formulations. They're allowing you to have problems. Go through the whole bit and you're like, think science. Get it? All right? Everyone got that? Okay, let's move on. So what happens with UV radiation? What happens to it? UV radiation has sufficient energy to cause certain molecular bonds to break. Certain bonds break. Photons with wavelength of 242 can break O2. You got it? So it's a frequency. Certain frequencies cause certain damage. Wavelengths of 320 UVB can break ozone. So this will naturally happen. And so notice what happens. The UV radiation comes in essentially perpendicular to the plane of the molecule here. And it comes in and it's like Guardians of the Galaxy. Okay? Or if you're in Star Trek, it hits it with a photon torpedo. You follow? So it comes in and it hits it. And when it hits it, it starts to vibrate, and it can't take it any longer and it snaps. It breaks the bond. Follow? Okay? That's how it works. It comes in at a certain frequency, and depending on the molecule, and each molecule has a specific area where they vibrate and break. So essentially, hits it, can't, and it pulls apart, falls apart. So that's what happens. This naturally happens in the environment, by the way. But unfortunate with some of the habits we enjoy as people, we've caused more damage. So let's look at the UV. Okay? So this is what's happening. These are UV A, B, C, D, right? A, B, C, sorry. C's blocked. So we're really concerned about what A and B, all right? For the most part, all right? Doesn't mean that C isn't important, by the way, because if there's a hole in the ozone, and wherever that hole is, right, you're going to be concerned about what? C. So if you live in an area where there's a hole in the ozone, and there is a hole in the ozone, then yeah, that tricky formulation with the C in it is a good idea. Does everyone follow? So here it breaks them, and here's what it looks like. As life, nature, God, creation, evolution, whatever you choose to believe, would have it, there is a different impact depending on your ethnicity with regard to skin, the effect of UV on the skin. Okay? Let's read the verbiage first, then we're going to talk about the chart. All right? When UV radiation is absorbed by skin, lower energy UVA light removes electrons from molecules such as water, creating free radicals and other reactive oxygen species. Translated, when UV attacks matter, it creates radicals. That's the bottom line. Radicals are bad actors. Radicals are the species that cause degradation to skin and other materials around us. So radicals is something we don't want to produce, okay, in this fashion, okay? There are helpful places where radicals are produced, but in this particular case, that's what happens. So UV light comes in, it attacks your skin, and when it does that, it creates a free radical. A free radical is a lone electron, and as it happens for molecules, they don't like to sit alone with a lone electron. They prefer to be paired. And so when it's unpaired, it is seeking out a way to be paired. And so what it will do is attack your skin, and it will collect an electron from it, but now it's transferred the radical to your skin. And then your skin continues to unzip or cause other problems trying to stop that radical process. Does everyone follow? Okay? It's a little bit like perhaps a game of hot potato, where the potato's tossed here. Say, I don't want it, yikes. You toss it to the next person, yikes, and it keeps transferring until it falls apart. Follow? Cause some skin damage. So that's what happens. UV light attacks it. Higher energy UVB causes chemical bonds to break. So in that particular case, it goes in and it just simply breaks the bond. So A comes in and as a radical and causes it to hot potato unzip. B comes in and simply breaks the bond and then it unzips. Okay? Follow? So DNA molecules are damaged by free radicals or UV absorption. Either one's bad. Follow? So we had a free radical or simple bond breaking. This results in the release of melanin. Know that. I always ask that question on my exams. That last statement on this slide with skin damaged by UV, I always ask that question. All right? And each time someone always misses. I can always tell who was present that particular day about who misses that question. I put it on there, and that tells me who missed my lecture. I can just go down and say, there's absent, absent, absent. You get it? I always have this on there. Okay? So that last statement, DNA molecules are damaged by free radicals or UV absorption. This results in release of melanin. The compound gives the skin its color, kind of a tan. Getting a tan. You get it? A yellowing is what happens. All right? Okay. So now let's look at the chart here with regard to how this works. We'll make it. Depending on your ethnicity, notice here, black females and black males, the lower is better on this chart, by the way. As you read this chart, if it's down, that's good. If it's up, that's not good. Have fewer incidents, if you will, okay, are less likely to be affected by UVA and UVB without skin on, okay? White females are more likely to be affected by it. White males are more largely affected by it. Now, tomorrow is February the 14th. It's Valentine's Day. Yeah, a lot of people like to give Valentine's Day gifts. That's your thing. If you happen to have a friend, you're dating a white male, or have a friend who's a white male, and you really want to give them a great Valentine gift, buy them some skin block. Okay. That's the moral of this story. Okay? You get it? Okay? All right? That's it. This is just the way things worked out. Follow? So there you go. Say, here. So what? Okay? You got it? All right? This is what happens. So you want to be aware of that, which means that you want to wear sunblock. You got it? When you're out, you want to wear sunblock. Okay? If you're going for a walk, wear your sunblock. It's very important. Doesn't mean that this doesn't happen, but the nature is as it has it. Okay? All right? I was in Hawaii for a while. I put on sunblock. Okay? All right. So what are biological effects? We've already mentioned this. We're going to talk about them again. UVC radiation is the highest energy, okay, and is absorbed completely by oxygen molecules, including ozone. So we're less concerned with it, correct? But we are concerned about UVA and UVB. UVB is partially absorbed ozone. It breaks O bond. Some UVB reaches the Earth's surface where it's rapidly absorbed by your skin. That's why you put on the sunblock to keep you from doing it. And notice what happens. It's kind of the epidermis, right? UVB. So it kind of gets here, and you'll know that right away. Okay, you'll start to see the spots and discoloration and things of that nature. So UVB effects are more noticeable if you kind of pay close attention to your skin. Okay. Bald head men should wear caps in the summertime. Yeah, so if you see me walking around with my cap on in the summertime, I'm really not trying to be cool. I'm not. Okay, I already know that. I passed that point, right? But I'm concerned. I won't be able to see all those the effect of UVB on my head. Okay, it's reality. Okay, I see some others have that same thing going for us. Okay, you got it. It's true. All right, I'm a bald head. Okay. All right. So this is important. I need UVB on my head. Sunblock, okay? Or cap. All right, UVA is not absorbed, okay? Less energetic, but it penetrates deep in the skin and causes damage in the underlying tissue. you won't know this is happening for a while. Okay? So that's what happens. And this all has to do with the difference in the frequencies of these, okay? The energy, overall energy of them. So the difference in energy is why we see these effects. Skin cancer, the facts. We're going to read through the verbiage first, then we'll talk about the chart. And again, chapter 3. I remind you, chapter 3, the slides are your complete study guide. There are questions from absolutely each of these on the exams, always, with chapter 3. Most skin cancers are limited, and these bullet points, I use these a lot for true-false type questions. The bullet points here. And for the most part, most of them look just like this. I cut them, I paste them, I put them right in there. Okay? Occasionally there'll be a multiple choice, but it'll be a multiple choice. It'll be a true-false that's really turned into a multiple choice. You get it? Okay? So this slide, I almost always pull these bullets. Most skin cancers are linked to exposure to sunlight. Voila. True, false? True. Get it? Skin cancer can appear in any age, but is more common in older people. Why? Why is that the case? Because age is catching up. And so the biology is starting to change, which means the ability to fight it is not quite there. So it's important that you look out for grandma and grandpa. Yeah, grandpa I just want to sit out in the sun. But please put on sunscreen, grandpa. Why? I've never put on one now. I'm 98 years old. No sense starting now. Now would be a good time to start. Okay? Because it's worse. You get it? As age. Okay? All right? Skin cancer can develop many years after repeated excessive exposure has stopped. You know the answer to why for one reason. What's the one UV? Is it A or B that might be causing this later effect? A. It gets there and you didn't know it was there, right? And it just slowly started to do its thing that you couldn't see, you couldn't detect. At least when I go out in the sun, if I look in the mirror or put my cell phone up and take a picture of it, I can see whether or not I've had an effect of it, right? That's UVB, but I can't UVA. Very good. Let's see. Cancer can arise in different types of skin cells, right? Those are basal, subcutaneous cells are common, but seldom fatal. These are seldom fatal. Cancer, okay, all right, is in the melanocyte cells. This is what we worry about, and okay, here. Now, we also type true and false. Is it the same in each ethnic group? No, it's not. Follow? Okay? So you want to be aware of that. Although some UV exposure is needed to produce vitamin D, this question is always on the exam. This question about vitamin D. All right, it's always on there. It almost always asks something like, is there a helpful, which of the following is a helpful application of UV? And the answer is always production of vitamin D. Okay. Too much exposure leads to cancer and eye disease. That's the key. They're helpful, and that's why, again, we talk about the helpful areas of chemistry on the electromagnetic spectrum. These are helpful areas, but too much exposure. So the real key when it comes to UV is limited exposure. So here, let's see what would happen here. This just kind of shows the disease, the possibility of disease of A, B, and C. Vitamin D is where you get deficiencies right about here. Skin cancer is here. And there's not much risk here in UV. B isn't so bad. So it's A and C is taken care of by the ozone. So this is what we're really trying to protect ourselves against, right? And this is where when you're young and you visit the beach at spring break, right? And you have a ball and those types of things, year after year being in school, your parents are trying to say, please, you've been in school 9 years and you've been to 9 spring breaks, please get out. Okay, so after 9 spring breaks, this is what's happening, UVA. So when you go to spring break, take some sunblock with you. Got it? There we go. This is the UV index. I'll have to update this slide in Canvas. It's missing this part, the reference here. But be aware of this. So we'd like to at least know and be familiar with what's extreme violet. You can almost remember that, can't you? Right? Follow? The extreme is violet, right? The low is green. Green's go. You get it? Extreme violet. Everyone follow? So you want to be aware of these. This is a color index. This index is used a lot. I don't know in Michigan, anybody pays attention in Michigan to this index much? Not too often. But if you're like in California, if in Hawaii, you pay attention to the index. You almost read it before you go out for the day. Determine what kind of sunblocks you're going to put on. So it's normal here. But Michigan, my observation is not too many people think much about it. Okay? Important facts to consider with most index of forecasts include ozone concentration in the upper atmosphere, elevation, and cloud coverage. Cloud coverage helps block a few effects, right? The ozone, it filters out what? C, right? And you also want it to be functioning well, so it takes out its fair portion of B. Does everyone get it? Okay? And elevation. So these all have an impact on it. Okay, so with that, now that you understand UV, UVA, UVC, you understand electromagnetic spectra, you also understand about the troposphere, stratosphere. Let's take a look at some other impacts of the atmosphere and how it impacts life as we enjoy it on Earth. This scale here just shows you how things are, and you've already looked at the scale in another fashion in chapter 1 or 2. And you have your ozone layer here, and you see about where the ozone layer is about 9 meters to about, that's 20 meters. So between 9 and, kilometers. That's about right, yeah. So here, so you have the ozone layer in this region. Now, for the verbiage. It's kind of talking about, have you ever seen a plane land in Denver? What we're really talking about here is that the air affects friction. So what you have is air molecules moving around, and that's important too. The movement of the air molecules is going to make more sense to you when you look at the next slides. But the movement of the air molecules is what affects some of the other features that leads to some of the bad things, well, not so good things, that are happening to our environment. Okay, and it has to do with air current and things of that nature. So understanding this particular point is very important. And for the most part, I usually ask you something like, you're in Denver, does the egg boil? Does it take more energy to boil an egg? The answer is yes, okay, because of the pressure. So there are few air molecules at that height, reduce the amount of friction, so a greater amount of energy is needed to stop the plane. That's the key thing. Where there are fewer air molecules, it requires more energy to do the work. That is kind of the take-home message here, okay? There's less air pressure at this altitude. Okay, why does it take longer to cook an egg in Denver than in New Orleans? New Orleans is closer to sea level, therefore the egg will boil faster. Water boils with the vapor pressure. This is something I almost always ask too. Water boils when the vapor pressure of water molecules exceeds that of the localized pressure. True or false? Got it? This point here. Water boils when the vapor pressure of water molecules exceeds that of the localized pressure. So whatever the localized pressure, when it exceeds that, it boils. Okay? That's because there's less air pressure at the higher altitudes. More energy must be supplied longer times to get the temperature of the water is high enough to boil the egg. But this is the take-home message. Where thinner air, fewer air molecules, less resistance. Follow? So when the plane is moving, it requires more energy to stop it because where there are more air molecules, they're actually fighting against it. Each time you go for a walk or you move around, you're actually fighting against air molecules now, okay? But you don't feel it. You're accustomed to doing that, okay? That is normal, okay? And so the fewer the air molecules, it takes less for you to move through, but it takes more to stop. Follow? Okay? Here, when the water boils, when the vapor pressure of the water molecules exceeds the localized pressure, if the pressure is X and it exceeds that, then it's going to boil, and that's important. This is important to understanding how we move certain bad actors, radicals around the globe that cause problems with greenhouse effects. You're going to hear more and more about greenhouse effects, ozone, and these types of factors. Okay, got about 20 more minutes here. I think we'll go as far as we can today. I think we'll be able to finish it. Let's take a look at this slide. This slide, the ozone layer. Looking at the ozone layer. So now we have the ozone layer here, and if you notice on the slide, we have on the picture on the left, we go from your ozone concentration increasing from left to right. And then it just shows the altitudes here in terms of miles and kilometers. Okay. And you note that somewhere about 15 kilometers is where ozone really resides, between 15 and 30. Okay. You also note there's a little bit of ozone in the troposphere. This is called a secondary pollutant. Note this, write it down. When ozone is in the troposphere, it is a secondary pollutant. That was on your first exam. Okay. Ozone in the troposphere, it is called a secondary pollutant. Secondary pollutants are those that interact with other pollutants to cause an effect, to have an effect. Okay. So we really want to protect the ozone layer because it's important. Now you know the UVC, okay, and balancing our way of life. The ozone layer is a region of the stratosphere where maximum ozone concentration is. Concentration of ozone in the stratosphere is 12,000 parts per billion as compared to 20 to 100 in the troposphere where it is considered an air pollutant. Be aware of that. 12,000 parts per billion. Okay? Here we show you ozone and oxygen. They have similar structures and they work in tandem. They work together in the ozone layer to block UVB and also to continually produce ozone to protect the environment. You're going to learn that here in Chapter 3 as well. This slide, how is ozone concentration measured? And this is an awareness for you to know how it's measured. It's measured in DUs. They're called Dobson units. The corresponding pressure, the compressing the ozone, it's 0C, the 3 millimeter stick of slab. I don't need you to know that definition, but I need you to know that it's measured in Dobson units. That's important, okay? And the other part that's important is the ratio here. For example, if it's 3 millimeters thick, that's 300. If it's 5, it's 500. So if it's 6, it's 600. Does everyone follow? That's what I expect you to know. That what it looks, the relationship there. And that's called a Dobson unit. So this is how we measure ozone. That is the bottom line here. So look at the number of Dobson units. So you'll know, so there's a standard number of Dobson units that's required to protect the environment. And so they measure to where those numbers are going up and those numbers are going down. When those numbers are going down, they call it ozone depletion. Okay, you follow? Right? So restoration is when those numbers go back up. Right? And what you like to have is this steady state. There's always a state of decrease, increase. Okay? But it has to stay between a certain norm for protecting us from UVC. This is a part that we're going to practice on Monday when we talk about Lewis structures. Understanding how UV light destroys ozone, Lewis structures. And we're going to practice Lewis structures on Monday. Okay? But we're going to talk about it now, about what it is, and we're going to practice more on Monday. Does everyone follow? Okay? So be aware that we will practice this and we will discuss this more on Monday. So with the slide on understanding how UV light destroys and the Lewis structures, suffice it to say that the valence electrons are involved, okay, in the destruction of the ozone layer. They're called valence electrons, and we're going to talk about more about that on Monday. We're going to talk in detail on that, okay? So suffice it, make a note to yourself now that valence electrons involved in the destruction of ozone, okay? And we've already told you what the Dobson units are. We'll come back to the slide and practice this on Monday. But this is what the Lewis structures look like when they're all said and done. For the most part, in CHEM 102B, I don't ask you to do a lot of Lewis structures. The Lewis structures that I ask you to know and know how to do, most of them are on this slide. So this is a slide you want to take out and you want to post it on your board, on your bathroom window, on your game gear, take it on a date. If you memorize these, you'll do pretty good with the Lewis structures. Follow? All right? So we'll ask you, and we'll have these Lewis structures. Some of these will show up on the exams, and moving forward, not only on this, but going forward through chapter 6. Okay? So I suggest you practice drawing these, because these are the critical ones that you will see. Okay? Because these interact to cause either good things or bad things that happen in the environment. Okay? Some of the things that happen are actually natural to the environment, and we'll talk about those as well. The shape of the molecule will be described in chapter 4. Okay? We'll talk about that again in chapter 4. That's what I said. You'll see this in chapter 3 and chapter 4. Some molecules, like ozone, can be drawn with two equivalent Lewis structures. So this basically means this is called a resonance structure. It looks like, it doesn't quite look like this. It doesn't look like that. It looks like a combination. Ozone is OOO, and that's the resonance structure, okay? And so you can draw this one or you can draw this one. I suggest you learn to draw them both, because I might ask you to draw a resonance structure. So if you can draw these, you'll be ahead of the game in terms of the types of Lewis structure. But we'll talk more about this on Monday, okay? But for now, what we'd like for you to know is that these structures are either helpful or harmful to the environment. Ozone's helpful to have the environment. Chlorine in the environment is not good, and for HF in the environment is not good, because these form radicals that attack ozone and deplete it. And we're going to show you how it works on this slide. This brings us to the Chapman cycle. The Chapman cycle is where we use our understanding of Lewis structures. Whether you can draw them or not, you have to understand what they do. So for the most part, Lewis structures produce the destructive species to the environment. Their Lewis structures produce radicals that deplete, that work against what's called the Chapman cycle. The Chapman cycle is how ozone is produced and regenerated in the environment. And this cycle you will want to pay attention to and learn. Okay? This set of reactions that occurs naturally in the upper atmosphere results in a steady state concentration of ozone in the atmosphere. As long as this is working well, we get ozone in the atmosphere and it stays there, it works well. Let's go through each step. We have O2 and we have UV photons. Anybody know where we get these UV photons from? Other than Guardians of the Galaxy? Where do we get the UV photons from? Just take a bold guess. Where? This is up in the atmosphere, up in the stratosphere. It's almost to go into outer space. Where do you think we can get a real strong source of energy from this in outer space? Sun. There you go. So if you see UV photons, we are thinking what? The sun. Got it? Okay? So everyone follow. This is where we get this energy. So we have O2, okay, and at this wavelength, nice frequency for these photons, when they hit at this frequency, to break it apart into what's two oxygen species. Okay? This oxygen radical if you see O, there should be a dot here. This author didn't put a dot in it, and it drives me nuts. Okay, so we have O here. This O attacks O2. And voila, we get O3. And it goes around and around in this subcycle. And this is good. We're producing ozone, we're depleting it. We're producing, going away. This is what we want to see happening. Okay? But you're going to need more O2. So as nature designed it, if you hit it with photons, where do we get these photons from? The sun. Very good. At 320, we can take ozone, and it'll collide with O, and it'll produce more oxygen. Okay? So in this case, we're taking O3 out, but it's producing oxygen. What do you think happens to this oxygen once we produce it? The 2O2. What does it do? Goes back into the Chapman cycle as O2. Does everyone follow that? So as long as this is happening in the environment, it's great. Follow? This is the natural cycle for ozone and O2 up in the stratosphere that protects us from UVC. All right? So, but here's what happens. Occasionally, we throw one of the Lewis dot structures into this, and it breaks the cycle. So it either sucks oxygen out. If it takes oxygen out, we can't make O3. Does everyone follow? Does everyone see that? If it attacks O3, then we can't make oxygen. And that's what happens. And when that happens, it depletes the ozone layer. Okay? Does everyone follow? Okay? That's what's happening. So we have these Lewis structure radicals that attach O2 or O3 in the stratosphere, and it breaks the Chapman cycle. Got it? So how do we deplete ozone? We have these Lewis structure radicals that attack oxygen or O3 in the stratosphere, and it breaks the Chapman cycle. And when that happens, we deplete ozone, and that's what's happening to us today. Okay. I think you may be exhausted. We will complete this on Monday, okay? We'll finish this one on Monday. All right? And we will review and practice some Lewis structures.